Hello, hello, hello. Today we're going to be talking about the running median problem off of Edugator. This is going to be a solution video. So first of all, I hope you guys remember from your programming quiz 3 what a median is, but just to quickly review, let's say you have a sorted list of some number of elements. Let's say we have 3 elements. The median is going to be the middle value in that list. So our median would be 2. Close this. If we had 4 elements in our list, say, we could do 1, 2, 3, 4. Then our median is going to be somewhere in between the 2 middle elements. To get that in between number, we would just add them up, divide by 2 to get the average, and we would get 2.5. Now, the difference with this problem is they're not just giving us a list and finding a median. What we're getting is actually what you can call a data stream, and we're going to have to return a vector of medians for each new number in the stream. So if we go through their sample input and output, you don't have to read the explanation, I'll just say it right here. But let's say we have 1, 42, and 33. So first we're going to get 1 passed in. And so 1, that's just going to be, 1 is just going to be our median in this case because there's no other items in the list. Now we're going to pass in 42. Our list looks like 1 and 42. Our median is going to be somewhere in between these two. It's going to be the average of them. So 1 plus 43 over 2, 1 plus 42 over 3. 1 plus 42 over 2 is 43 over 2 is equal to 21.5. So that's going to be our second median. And finally, we're going to get the third number in our list, which is 1, 42, and 33. However, we know that our list has to be sorted to actually find what the median is. So we're going to turn that into a sorted list. And then add this. And now our median is going to be 33. So what we would return to the program would simply be, let me make sure this is fully visible. Sorry, it's off the edge. What we're going to return is going to be 1, 21.5, and 33, which we can see in the sample output right here. Okay, so the naive approach might just be to straight up implement this in our code. So what we would do is say whenever we get a new number, we would completely sort the list to make sure that it's in order that we want. So like if we had like 1, 3, 5, we're at that current, 1, 5, 3, that was our current state. We would first sort it into 1, 3, 5. Then we would somehow iterate to the middle element, put that in our list, and then call it a day. However, this isn't really the most efficient way to be doing this because we're going to have to call sort. And sort is a decently expensive operation. What you'll soon learn is that any sort at its most efficient is going to have a time complexity of n log n. And because we're going to be sorting once for each of the n elements in this list, we're going to end up with a time complexity of something like n squared log n in the end. And that is not great. What if there was a better way to do this? Well, as I hope you have assumed from the title of this unit, there's actually a really clever way we can do this by using heaps instead of just working with the list directly. So let's pull up an example and figure it out. Or let's start, So I'm going to pull up a slightly modified version of the first Edugator test with easier numbers just to make it a little better. So this is the first Edugator test. Let's do these first 5 elements. I'm going to replace the 89 with a 5 so it looks nicer. So we got 2, 5, 1, 3, 4. Now, how would we go about splitting our list into heaps such that we can really easily find the median? Well, let's first of all sort this and think about it this way. We're not gonna need to sort it in the end, but for now let's imagine it is. So let's see, we got 1, 2, 3, 4, 5. Well, we're trying to find the middle element, right? So wouldn't it be nice if we had some split to where we had the lower half of the list and we had the upper half of the list, and we could get the biggest number from the lower half and the smallest number from the upper half, and then if it's an even list, we could take the average of those two and get our median, or we could just pick the biggest number of the half. So let's do that. Let's define, we're going to have a lower heap and we're going to have an upper heap. Now, because we want the biggest of the small numbers out of the lower heap, we're going to make it a max heap. And because we want the smallest out of the big numbers from the upper heap, we're going to make it a min heap. Excuse me. So let's draw out what that would look like. Again, we're assuming it's sorted. And arbitrarily, we're just going to say the lower heap is always going to be bigger than the upper heap if we have the chance, just so that way we don't have to figure out which of the heaps to pick from when we're doing this problem. So let's say we've got so we want to surface the biggest number. It's a max heap, so let's say it looks something like this. The order of the children doesn't really matter. It's still following the heap properties because the biggest number is always on top. And then our upper heap would have 4, the smallest number, and then 5 right there. And so now, when it's time to get our median, we could just say, okay, well, my lower heap is bigger than my upper heap by 1. Therefore, this must be the middle element. Perfect. Okay. What if we had a 6th element? Well, that would be pretty easy. We would just put the 6 in here, and we could still figure out what to put in now. So we'd average 3 and 4. So 3 plus 4 would give us over 2 would give us 7 over 2, which would give us 3.5 for a median. Of course, our heap isn't sorted, so we need to figure out some way to know which of the two heaps to put our data into as we go. The naive solution might be to say, oh, okay, well, I'll just put the first thing I see in the left heap, the second thing I see in the right heap, then the left heap and the right heap, and so on. But we're going to run into an issue pretty quickly, as we'll see. So if we insert 2 here, then we insert 5 here. It's all good so far. This makes sense. We insert 1 here, still okay. Insert 3 here. Oops, we have to heapify, but that's fine because the heap's doing that for us. And then finally, we get to 4, and we say, oh, well, we're just going to put it on the left. We're going to have to heapify, so we'll get 4, 1, 2. But we run into a problem because, as you can see, 4 is actually bigger than 3. So you could say, oh, okay, well, there's this point. Well, if this ends up being bigger than this, I'm just going to move this over here. So let's say, okay, we're going to pop 4 off the heap. We'll end up back with 2 and 1. We'll put 4 on top, or sorry, we'll keep 3 on top here. We'll have 5 and 4. And now we have this, but then this is going to break our original statement where we said, let's make sure that the size of the left heap is always bigger than the size of the right heap. So then you could say, oh, well, then I'm just going to move the thing from here over here to rebalance. So we'll say, okay, we'll remove the 3. We'll put it over here. So now we'll have 3, 1, 2. And then we'll have 4 and 5. But then, okay, so we're alternating, right? We're saying we'll put it in whichever heap has the smallest number of items. Let's say we add, I don't know, like 0 now. What's going to happen? Well, if we try to put 0 in the right heap, we're going to see that, well, that's clearly not correct. And then we'll have to move 0 up. We'll have 0, 4, and 5. Then we'll have to move this over there. And it ends up being this big, huge mess with a lot of ifs and a lot of cases. And you're going to have to come up with a balance helper function and all sorts of stuff to make sure you're putting in the right heap. But what if there was an easier way? What I propose is you buffer everything through the lower heap and move it each time. So that way, you're always making sure you're keeping the elements split properly. So what do I mean by that? Well, first, we'll put something into the lower heap, always by default. And then, after the heap heapifies itself and sorts itself, we can move it to the upper heap. So we're going to move the 2 to the upper heap. Now we have it here. And then, because we told ourselves, oh, we want the size of the lower heap to be bigger than the size of the upper heap, we're going to move it back. And right now, that seems pretty silly with just the element 2, but we'll see why this is good later. So we'll move 2 back over, and now we have our median. Nice. Okay, so now let's add 5. So we'll put 5 into our lower heap. We'll see, oh, it's a max heap, so we need to heapify up. So we're going to get 5 and 2, and then we'll push this, or we'll push this over to our upper heap. So we'll have just 5 here, and then this is going to go away. We reheapify, we get 2. Great, and now we can average these to get the median. So this is still working. And now, because these are even, there's no need to push this back. So we can just get the average between both of these. Okay, so we have 2 and we have 5. Now let's do the same thing, and let's add 1 to our lower heap. And as we can see, 1 goes right here. Nothing needs to move around. But anyways, we're going to push the 2 into this heap. So now we're going to resort everything. We're going to be left with 1 over here. We're going to be left with 2 on top here and 5 here. And then we're going to say, okay, now let's put this back over here. Again, a little redundant in this case, but by keeping the sizes the same, and then, by keeping the sizes the same and ensuring these things, even though you're going to be doing some movements that maybe you didn't have to do, you could have recognized, okay, I've got it like this, I'm going to do this. You're going to cover all of the edge cases, and you're just going to make it work in every case with a decently simple algorithm where what we're going to do is we're going to put in left heap, left insert. We will move the top thing to the right heap. And then if we need to, we'll balance the heaps again by moving the right element back to the left. So what does that look like in code? Well, I have an editor up right here on the side, and we can get to work implementing this. Okay, so first, what do we need? We need our list of medians to return. So let's just make our vector of doubles. We will call it medians, nice and simple, and we will return medians at the end of our function. Next, we need our heaps. What are we going to do about that? Well, first, we want our max heap for our lower. So what does that look like? In C++, you can use the priority queue. That is going to be a type that is included in the queue standard header. And it's going to take in 3 parameters. It's going to take in the type that you want to store in there. And then optionally, there's 2 other parameters. By default, this is going to make a max heap for you. So we'll talk about what that is, but we'll call this lower for now. We want a max heap for lower, so this is our max heap. Now, what are the default parameters in here? If we expand it out, first will be the data type of the data you're trying to put in that heap. Then will be the container you want to store it in. By default, that's going to be a vector of the same type as you have here. And in this case, I'll just say a vector of ints. And then finally, some comparator function that the priority queue is going to use when comparing one item to another and determining how to order them. By default, it is going to be standard less. But because we're using names as standard, we can just say less, and we can say int because we're trying to compare ints. Now that is going to be a max heap. What if we wanted it to be a min heap? Well, it's pretty simple. We just swap the comparator. So instead of using less than, we use greater than, and we call this one upper. And now, without having to do anything else, this is actually going to be a min heap for us. And I may have mixed these definitions up, but I'm pretty sure it's less than greater. We'll see when we run the code. Okay, so we have all this. Now let's go through the elements in our actual array. I'm going to use a nice ranged base for loop just because it's easy. I will say for int num in array. And this is going to go through all the numbers in there. Now we can start implementing our algorithm. So like we said, by default, we're just going to put something in the left heap. So we're going to say lower.push. That's how you insert into a priority queue. And we are going to insert num. Now we are going to move the thing to move the root of max heap to the min heap. So this will account for times where we end up with something bigger on our left than we get on our right. And of course, if you want to like make this a little more efficient, you could add extra conditionals to account for cases where you don't need to do movements. But for this, just the simplest possible way forward, we're just going to move it anyway. So to do that, we can say upper.push lower.top. Top is going to only access the root of the heap, but it's not going to do anything to it. It's not going to move it. It's not going to delete it. It's just going to show it. To actually pull that thing off of lower, what we can do is lower.pop. And that's not actually going to give you the value. It's only going to delete it. So in other languages, you might be used to pop might also return the value. Not in this case. So we're going to get the value with lower.top, and then we're going to pull it up, pop it off of lower with lower.pop. Great. Now we have to do the size check, because remember, we're always saying we added a rule that we are going to make sure that if it's an uneven size, we want the lower heap to be the bigger one, because that's the one we're going to pop our top thing off of. So now let's move back if need be. So if our upper.size is greater than our lower.size, what we can do is simply do the reverse of what we did here. So we can say lower.push upper.top, and then we can do upper.pop to get it off the other stack. And now our heaps are evened out if they need to be. And finally, we can get the median. So if we can see if the lower.size is greater than upper.size, meaning we have some uneven number of elements, we know for a fact that the one extra element is going to be on the left, we can just say we're going to push back the, or because remember, medians is a vector, we're going to push back lower.top, because as we established earlier, we're making it so that the left heap always has the median if there's an uneven number of elements. So I will complete this. Oh boy, hold on. Yeah, I'll complete this. And then otherwise, we're going to have to take an average. And to do that, we could either add them up together, or we could take half of each to avoid overflow errors, which is what I'm going to show. So we can say we're going to return lower.top over 2.0 plus upper.top over 2.0. And note the 2.0 is important. That is because, actually, what does it matter about? To return to, oh, sorry. Yeah, I'm returning. I should be pushing back here. So we'll do medians.push back lower.top and then upper.top. And so why am I doing it like this? Well, first of all, we need to divide by 2.0 so we're not accidentally doing an integer division and running into issues with our numbers getting messed up. And then we're doing the division by 2 in each element so that if these add together, they're never going to overflow and mess up our final number. So with all that said and done, this should just work for us. Let's run it into Edugator and let's see how we do. Okay. All right, so Edugator freaked out and wouldn't run the test, but I pasted it back in. If I hit submit code, we can see it runs and it passes. So we get the proper output for everything. So that being said, thank you so much for watching. I hope this was helpful and good luck doing the rest of these programming problems.